with these slides. I don't think we'll get to the beauty part, but we're going to talk a little bit more about recursion. Okay? Recursion was finding a problem inside of itself in a smaller form, and then we use that smaller solution to build up a bigger answer. So everything is built in terms of tinier versions of itself. If you find a recursive problem, that's how you want to think about it. And we solved the problem of finding the factorial of a number, like 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. We noticed that the factorial problem was recursive. A smaller factorial exists inside of a bigger factorial. And we can use that to create a general solution for any factorial. So like 5 factorial, you see 4 factorial just sitting there. 7 factorial, you see 6 factorial just sitting there. And if we generalize that, we come up with n factorial. That's equal to n times n minus 1 factorial. Okay? And if you try out that example long enough, eventually you'll get down to a case where it stops making sense. And that is the place where you want to stop. You don't want to keep using this rule forever because it's in terms of itself, it would never stop. It would go on until the end of time. You need one, or maybe more than one, way to stop. And that's called your base case. And that's when you're done with recursion. That's the smallest problem you know how to solve. You can immediately give back an answer. And that will allow the recursive case to finally build itself back up. And so we talked about recursive factorial. We can make a function, because that's how you solve problems in computer science. We can make a function that's recursive, which means it calls itself inside of its own definition on a smaller version of the problem. Okay? And that will allow us to build up the factorial of any number correctly. It will keep trying to get to the base case. Like fact of 5 will call fact of 4, who will call fact of 3, who will call fact of 2, who will call fact of 1. They're all waiting on each other to do their stuff. And eventually you get down to the base case where, okay, fact of 1, it knows its answer. Let me build up from what I know. All right, I'll give back 1. All right, I was waiting on that. Let me multiply my 2 by that. Oh, I was waiting on that. I'll multiply my 3 by that. And it just keeps on building itself up until we get back to the place where we want it to be. We finally have 120 to go and print out. Okay, so this was a stack diagram that was showing us all the stuff that needed to be done. Okay, so yeah, let me prove to you, like, it's a little weird to think about this. Like, why does this function, which doesn't have any loops, somehow loop? How does it compute the right answer? How can we prove that? So let me try to explain to you why recursion works. You will have to wait until CSCI 26 to fully understand it. But yeah, let me give you a sneak peek of it. Recursion is related to something called mathematical induction. Maybe you've heard of that, or if you've taken CSCI 26 already, you have been forced to learn it. It's a way to prove that things are true over a bunch of numbers, mathematical induction. And so let's talk about why it works on just a generic problem P. Let's call the problem that we're trying to solve P. Okay, and all right, when you solve a problem recursively, you say two things. You have a base case and you have a recursive case, right? Your base case is saying, I know how to solve, if my problem is called P, I know how to solve P for some very small value, like the smallest value. I know the answer right away. If you ask for me to solve P of 0, I can give you something back. Like the answer is 0, the answer is 1, something simple. I don't have to do anything extra. And that's the base case. I know how to solve this version of the problem immediately. All right? The recursive case, when you write your recursive case, if you think about it long enough, what is the recursive case saying? But if you give me one smaller solution, I can build you up a one bigger solution. You see how I'm kind of reading the equality backwards? You give me n minus 1 factorial, I can multiply that by my n and give you n factorial. So we can write that in math. If you give me, like, P of n, I can use that and make for you P of n plus 1. I can make you the next bigger one. It's kind of like an if-then statement. It really is logical implication. So you give me P of n, if I get P of n, then I can give you P of n plus 1. All right? And so that's like how you would logically write what the recursive case is all about. And I should spell it out. It's not just recursive, it's recursive case. So that's your base case and that's your recursive case. Base case is saying, I immediately know how to solve problem P0. You ask for me to solve P of 0, I can give you back an answer. And the recursive case is saying, if you tell me the answer to P of n, then I can tell you the answer to P of n plus 1. Okay, like give me the one smaller factorial, I can multiply something and give you the next bigger factorial. All right. And so the idea is, with these two combined, let me prove to you that you can solve any problem P of n, P of 0, P of 1, P of 2, all the way to infinity. Let me prove that to you. All right. So for example, let's pretend that we're trying to solve P of 5. Let me show you how you can solve P of 5 with these two logical rules. Okay. So we can't immediately use the recursive case because we don't have a solution to something. Right? If I have this, then I can give you this, but I have nothing to start. Right? What can I look at, though? What do I have concretely in front of me? I have the base case. I always know P of 0 immediately, so I can write that down. Like, I know P of 0. I have that knowledge, okay? And now the beauty is I can use the recursive case. I can use this rule, because it was saying, if you give me P of n, I can give you P of n plus 1. Look at what I have. Set n to 0. Ooh. Then I can run this rule with n set to 0, and it will plop out for me P of 1. See that? That's what the recursive case is doing logically. If you give me P of 0, set n to 0, it will give you back P of 1. There's a way to build up the problem from a smaller problem, and here's my smallest problem. So I can build P of 1 from P of 0, and then I could run this again, because now I have right in front of me, I have the solution to P of 1. Ooh. So I can set n to 1 in the recursive case. I can run the recursive case rule with n set to 1. All right, if you give me P of 1, which I have, I can give you P of 2. That's what it tells you it knows how to do. So it can use that to make P of 2, and I think you can see the game you can play now. You can use the P of 2, now you have that answer. You can use that with the recursive case rule to build P of 3. See that? So this is how you would prove that it works for any number greater than or equal to 0. You can use P3 to build P of 4 using the recursive case rule, and you can use P4 to finally build what you wanted, P of 5, using the recursive case rule. And I think you can imagine that it will work for any number all the way to infinity. So that's the reason recursion works. That's the reason all this happens. And the beauty of it is, it might be not so obvious the way that I stated it, but you actually don't have to think when you're writing the recursive case rule, when you're implementing it. You can just assume, you can call yourself, right, on a smaller version of the problem. You get to assume that that gives you the right answer. Because this is just an if-then statement. Like, if I had this, then I can give you this, right? It doesn't mean I have to verify. Like, if I had this right answer, I can give you the next bigger answer. So you can just assume that it's going to work, and it will, assuming you have correctly built up the correct final answer, the correct bigger answer, okay? Because it will eventually get to the bottom and start building itself back up, one by one, until it gets back to the thing you really wanted, okay? So that might be a little hand-wavy and vague. You'll have to wait till a fancier class to learn more about that, but that is the power of recursion. Okay, any questions about that? Anything that's too confusing? All right. So with that in mind, let's solve a different problem now. I claim that there is a recursive solution to power computation. Like if you're asking to compute 2.5 to the power of 5, there is a smaller power computation inside of that one. Can you take a minute to find it? 2.5 to the 5, like write it out. Can you find a smaller power computation inside of this one? There's something for the power inside of it. So take a minute to think about that, and then we'll come back and talk about it. I think there is. Can you find the next smaller one? All right, do we see it? 2.5 to the 5 is equal to 2.5 times 2.5 times 2.5 times 2.5 times 2.5. So where's the smaller power computation? Do we see it? By half? I don't see any halves anywhere. But like, I don't know. This is multiplication, right? Bunch of multiplications. So 2.5 multiply itself 5 times. Can you find 2.5 multiplied by itself a few less times than that? You can draw parentheses however you want, but here. What's this? How would you write that out? 2.5 to the what? Yeah, so there's a smaller power computation. Do we see it now? Yeah. And then like here's 2.5 to the third. I mean, you can find it anyway. Like there's 2.5 to the third as well. 2.5 squared, 2.5 to the 1. I guess 2.5 to the 0 is technically there. Like it's times 1. You can always multiply something by 1. That always works out. But there it is. Does that make sense? So we can find a smaller power computation inside of a bigger power computation, which proves that it's recursive. Ooh. And that means we can generalize this. Right? We can generalize this. We'll make a function that works out just fine. But, all right, instead of, I don't know, let's try to do 2 to the 4th. See if this generalizes further, right? 2 times 2 times 2 times 2. Here is 2 to the 3rd, right? It always works like that. You can find a smaller power computation, a one smaller one. Like, there's 2.5 to the 5, there's 2.5 to the 4th inside of that. Here's 2 to the 4th, here's 2 to the 3rd inside of that, right? So, that can be generalized. So let's make a recursive case. You're asking me for a number n to the power m, where m has to be a whole number. Well, what is that? Let's say that 2 is the n and 4 is the m. How do we solve this? 2 to the 4th, that's equal to 2 times 2 to the 3rd. So n to the m is equal to n times n to the m minus 1. You see I'm reading that? Any questions about that? That will be the recursive case. That's the smaller power computation living inside of that one. Okay? So, let's see how far we can do this until it breaks down, because we have to find a base case as well, right? We can't have it multiply until the end of time. That won't work. Then our computation will never stop. Can't have that. So let's figure out what the base case should be. So let's try this out. 2.5 to the 5. That's equal to 2.5, right? According to our recursive case rule. 2.5 times 2.5 to the 4th. Just like this is 2 to the 4th is equal to 2 times 2 cubed. Okay? So that's our rule. And then, all right, this is another power computation. Let's split that down into 2.5 to the 4th. Well, that's equal to, following our rule, 2.5 times 2.5 to the 3rd. Right? Here's another power computation. So let's keep going. 2.5 to the 3rd is equal to 2.5 times 2.5 squared. Yeah? What's 2.5 squared? We can run that rule again. Why not? 2.5 squared, that's equal to 2.5 times 2.5 to the 1, the first power. And, all right, what's this? Do we immediately know an answer? Anything to the first power really is itself. But we could try to keep running this rule. This could be a base case, though. But, I don't know. 2.5 to the first power, that's just, well, let's keep following the rule. 2.5 times, let me give myself some more room. 2.5 times 2.5 to the 0. Which technically still works, right? Because that's 1. So, all right. That's just 1. This is 2.5. That's correct. All right. Does this keep working? Can I keep unfolding this? 2.5 to the 0. Can I follow this rule any further? That equals 2.5 times 2.5 to the negative 1. Okay, that's 2.5 over 2.5. That's equal to 1. Sure, that still works. I don't know. If I unfold this one, that's equal to 2.5 times 2.5 to the negative 2. So it's like 1 over 2.5. That's where it starts getting wonky and it doesn't make sense anymore. So I think let's just cut our losses. And I think a good base case would be anything to the 0th power. You ask me for anything to the 0th power, the answer, right, it's always 1. That's a good base case. That's where I can stop all this. N to the 0. You ask me to compute n to the 0. The answer is immediately 1. Okay? And that will correctly solve anything. Any power greater than or equal to 0. Are there any questions about how I discovered all this? You think you could do it too? Generalize the cases into a recursive case and then go searching for the base case? Any questions about that? Because now it's time to implement it. Let's do that for sure. This is lecture 30. Oops. My computer's running too many things, I guess. All right, so let me just make this small to begin with. We need this to be visible eventually. New file, lecture 30. And we'll call this POW, POW for power. So it'll be pow.pi. And we'll run it like this. We'll say, you call our function called pow. The first thing is the thing you want to raise to a power, and the next thing is the power. So it'll take 2 arguments, and that will compute 2.5 to the 5th. Okay, that's how we're going to do it. And it will be recursive. It will work out because that exponent, that's the thing that's getting smaller, right? Something always has to get smaller in our recursive call. And that's the 1. So let's compute this. And then we want to use it like this, like print pow 2 and 4, so 2 to the 4th power. What was 2 to the 5th, 2.5 to the 5th power? I have no clue. Let's compute it. All right. So def pow. That's going to take 2 numbers, right? The first thing is the number you want at the base. So that's like your n. And then the next thing is your exponent, so that'll be the m. So it takes those 2 parameters, n and m, and it computes, returns n to the mth power, I guess in Python notation, n star star m. Right? So that's how you can always check yourself too. Okay, so the job of a recursive function is to figure out first what case it's in. Are we in the recursive case or are we in the base case? So how do you know you're in the base case? Well, it looks like it's your second parameter. You check that. Is that 0 or not? So if m is 0, that means we're trying to take something to the 0th power. Anything to the 0th power is 1. So the answer is immediately 1, and we give that back to the user. Return 1. Okay? Otherwise, else, we're in the recursive case. N to the m is equal to n times n to the m minus 1. All right, so we have to go off and compute that. I think I did this for a factorial, like I saved the recursive computation in a variable like x. That's equal to, like I have to multiply my n by n to the m minus 1. So let's compute that. What is n to the m minus 1? Well, it's our function, pow of n and m minus 1 now. And then the result is n times that. right? The bigger result for the larger original power computation, it's one more. It's this one times our n. Return n times x. So that would be the solution. I used a separate variable just for fun last time to kind of like make it easier to think about, but you could just do this. You don't have to make a variable x, just call yourself in that return statement. So return n times pow of n and m minus 1. So this exactly corresponds to our recursive case rule. Return n times n to the n minus 1, which is this pow function call. Okay, does that make sense? Any questions about any of that? And for similar reasons, it's going to do the right thing. So 2 to the 4th, yeah, 2, 4, 8, 16, that works. You can always check yourself with normal Python. And 2.5 to the 5th is, in fact, 97.65625. And it works for anything. Pow of, I don't know, 5 to the 0, that's always 1, right? It hits our base case immediately, but otherwise it's going to use the recursive case for a little while until it gets to the base case, and then it builds itself back up. Okay? Any questions about any of that? This does only work, sadly, with integer, whole number, and non-negative exponents, because otherwise you'll never get to exactly 0, one at a time. But it works for those. Are we good with this example? Before I make it more complicated? Let's save the most complicated example for last. It is called divide and conquer. The idea of you can classify algorithms in certain ways, and a certain class of algorithms are called divide and conquer algorithms. And they are naturally recursive, right? So a divide and conquer algorithm, it's one that is recursive, and it's also one that breaks up its problem into equal-sized smaller problems. We didn't really do that with the power computation. It's like, all right, let's make a big power computation, and then one smaller, then one smaller, then one smaller. No, a divide and conquer algorithm would have split this in half. Done this one recursively, done this one recursively. All right? So that's where I'm going with this. So yeah, divide and conquer. It's recursive, and it breaks its problem into equal-sized subproblems. And like it breaks them into chunks. Maybe it breaks them up into 3s, into 2s, into 5s. Doesn't really matter. Usually the factor is 2. But that's what it means to be divide and conquer. So for example, I don't know, like I've got a bunch of numbers, like I've got a list of numbers. A divide and conquer algorithm, maybe if its factor was 3, it would split this up into 3 separate halves of the list. 1, 2, 3, about the same size, as close as possible. And then it would go off and it would solve those, okay? And that would bring back the answer to one bigger solution. Okay, that's the idea. So let me show you just a very simple example of this. It is the problem of adding up just all the elements of a list. Let's pretend we have a list, and let me show you how to use divide and conquer to add up all the elements of a list. First, let me give you an example. Before we do that, let me give you an example of the quintessential divide and conquer algorithm that you'll see one day. It's called merge sort. So here is a unsorted list, 8, 6, 7, 5, 3, 0, 9. And here's the idea of a divide and conquer algorithm. It would break up this list into 2 halves, and the goal is to sort it, so to make it into increasing order. Here's what it would do. It would break this into 2 halves, and I don't know, let's make it even just to make it easier. Let's put a 2 at the end or something. It would split this into 2 halves, so it would make the list 8, 6, 7, 5. And it would make the list 3, 0, 9, 2. And then it would recursively sort those. And you get to assume that it's going to work, so the power of recursion would sort this smaller list and this smaller list. You get to assume that that works as long as you build up the final answer correctly. So this would make 5, 6, 7, 8. And this one would make 0, 2, 3, 9. And then the final job of the sorting function, the divide and conquer function, like it divided them, it conquered them, the conquering was sorting them, and then it builds up the final original answer that you needed. So it will merge them back. That's why it's called merge sort. It merges these two sorted lists in this way. It's like, all right, let's look at the first pieces of all these, like 5 versus 0. Okay, the 0 wins. Okay, now it's 5 versus 2. Oh, the 2 wins. All right, now it's 5 versus 3. The 3 wins. Okay, now it's 5 versus 9. The 5 wins. Now it's 6 versus 9, and you get the idea. 7, 8, 9, and it builds up the final list. And so that's the idea of divide and conquer. Chop your problem in half, or in thirds, or in fourths, or in fifths, and solve them separately, recursively, and then finally build up your answers using those smaller sub-problem solutions. Like these are smaller sorted lists, you can build a bigger sorted list from those more easily. So that's divide and conquer. And my silly example, we're not going to do merge sort. That would be a lot. That would be like a CSCI 41 kind of topic. Let's add up all the elements of a list. Let's do that in divide and conquer style. So let's take that same list. Why not? It was 8, 6, 7, 5, 3, 0, 9, 2. Let's divide it in half. Chop it in half, right? And we'll make 8, 6, 7, 5. And we'll make 3, 0, 9, 2. And we will conquer them separately. So we divided them. Now we need to conquer them. And you're going to solve the problem on those smaller lists. What is our problem? It's add up all the elements of a list. So I have some smaller lists. Let me recursively add up all their elements. So what would be the solution to this one? We just get to assume that the recursion takes care of it for us. This is going to give us back what? This is 12, 26. 26. And this is 12, 14. 26 and 14, and if you add them up together, the final solution is the sum of both of these, right? The sum of everybody is the sum of each of those smaller lists. Oh no, I just froze PowerPoint. There it goes. You add them all together at the very end, and then you get 40. The idea? So that is divide and conquer. That's how it works. But the idea is it's not going to stop here. Like the recursion, it's going to do the same problem. It's going to divide and conquer that smaller list. So it's like, I don't know. It's next going to try 8, 6, 7, 5. It's going to chop those in half, right? And then it's going to recursively solve 8, 6. What's that sum? 7, 5. What's that sum? It's going to keep chopping these in half as long as it can, right? It's going to make the list with just 8 in it, the list with just 6 in it. And if it's ever odd, like you're trying to sum 8, 6, 7, it'll chop this in half not perfectly. Like it'll take 8, 6, and then it'll take 7. And so eventually, you might get to a point where you only have, eventually you're going to get to the point where you only have one element in your list, right? And our original problem was we needed to add up all of the elements of that list. So how do we do it? What is it? If I just have a single list with one element in it, what is the sum of all of its elements? Everything inside of it? I don't need to divide it anymore, right? That can be our base case. Base case. If you ever end up with a list of just size 1, then, all right, let's say that the answer immediately is just that element, whatever's inside. So like it's a list with an element inside of it called, I don't know, E. The answer is E. Whatever was there. Does that make sense? So that's the sum of all the things in that list. If it has size 1, there's only one thing there. I guess, though we'll never get there if we start with a normal list, the user might eventually ask us to sum all the elements in an empty list. And that could be another base case. Like the answer is immediately 0 if somebody asks you to add up all the elements in a list that has nothing in it, right? So that could be our answer there. But that will do it. That's our solution. So our recursive case is split in half recursively solve to get the sums of those smaller lists, add them together, that's your final result. The base case is, there's two of them, is single element list. That one element is the sum of all the elements. Empty list, 0 is the sum of all the elements. Okay, and we can use len. You can immediately get the length of a list with the len function. Okay, any questions about this idea before I go to code? This is a good divide and conquer example. Divide and conquer .py. And so the idea is the user is going to give us, like, I don't know, what do we want to call this? Add list, sum list. And the user is going to give us a list, 8, 6, 7, 5, 3, 0, 9, 2. And it's our job to give back 40. So we can like print out that, print the 40. Okay? And it should work regardless of whether the list was even or odd. Like, if it was odd, you can't chop it in half perfectly. You'll make one list that's one larger than the other. That's fine. That's totally okay. So if we get rid of the 2, like there should be 38. And then the sum of an empty list, that's 0. Okay, so that's the kind of thing we want to make. And so let's make our function SumList. SumList. It takes a list. Let's call the list L, capital L, why not? And as usual, it's recursive. It's divide and conquer, which means if we have something, we're going to chop it in half. But if we have a base case, we should still be checking for the base cases first. If we have one of those, we immediately know the answer, just like for POW, right? If we are in the base case, we immediately know the answer. We don't have to chop anything in half. It's impossible to chop these anymore anyway. So let's figure out if we're in the base case. So if the list is empty, if len of L, right, that will give you the length of the list. If the list is of size 0, then the sum of all the elements is 0. Okay, so that's one case, one base case. Elif len L is 1, then we know that there's only one thing in the list. The sum of all of the elements is that element. So return L of 0, the 0th thing in the list, right? Because the indices start at 0. Just return that thing. If it's 5, the sum is 5. If it's 42, the sum of that list with just 42 in it is 42. Okay, else, that's our recursive case. First we divide, then we conquer. All right, step 1, divide. Step 2, conquer. So we need to chop our lists in half. Chop L into 2 halves. Okay, is that how you say it? Halves with a V. So how do you do that? There is a way, and I don't think I've taught this to you yet. So let's go to the REPL real quick. If you have a list, let's say L is equal to 1, 2, 3, 4. I can get the length of L easily, right, with len of L. I would like to chop this list in half, though. So I'd like to take just the first 2 elements of it, and then the last 2 elements of it as well, and make 2 separate lists. There's a quick and easy way to do that in Python. You can like take len of L, divide it by 2 so that now you have the number 2, and you can use the following. If you use these brackets, like you know that you can get L of 0 very easily, L of 1 very easily, just as normal, use indices. In Python, though, you can give a range of indices. So here's what you can do. You can say, I want a list from L from index 0 all the way to, but not including index 2. You can use a colon there. You see that? So that takes the first 2 elements. It takes everything from index 0 to 1 before index 2. It's like range where it's 1 before the last element. So this is inclusive. This is exclusive. And so that's how you can get the first list. And then the second list, you can get it from this. I want the list 3, 4, right? I want to chop it in half. So where is this? I want it to start at index 0, 1, 2. And then I want it to go until, but not including, index 0, 1, 2, 3. I want to take the 3, so I would use the number 4. That would be the one after it, but I don't want to include it, right? and that will get the list, and it will chop it in half. Does that make sense? So how 0 is very obvious. 4 is 1 plus the length, or 4 is exactly the length of the list, so that's len L could go there. And then the 2, that's in common here. You can get the 2 by dividing the length in half. So that's how you can chop a list up, all right? So let's do that. Let me show you how. So let's call it size. Size equals len of L. And let's do it like this. With this idea in mind, the first half, that's equal to L, starting at index 0 always, because that's the start of every list. How do I get it up until the halfway point? Well, it's up to the size over 2, right? Len over 2. That will give me the 2 there. Size over 2. Okay? That's the idea. And for reasons, just in case this was odd, like if you divide 5 by 2 in Python, it gives you 2.5. That index doesn't exist. So you can use 2 slashes to chop it down to an integer. Or you could round it, but I'll use 2 slashes. Okay? So that's the first half. And then the second half is L from something to the size, right? The size is the 4 there. That was the length. And keep that. But we want to start from the 2 this time. And the 2 generalized was this size over 2 concept. Okay? 2 slashes to make it an integer. So that will be the first half of the list, and this will be the second half of the list. Does that make sense? And then we want to recursively solve the problem, right? Divide, conquer. So we want to recursively call some list on the smaller halves. They're smaller, which means it's going to work out. The recursion will work. It's guaranteed. If you build up the answer correctly, it's going to create the right thing. You will get the correct answer for these smaller things. Recursively call some list on the 2 halves. All right, so I don't know, first half sum, that's equal to sum list ourselves on the first half. And then second half sum is equal to sum list on the second half. We get to just assume. We don't have to think about anything. We just assume that these are going to give us the correct sums on the first and second half, right? That's what this logic can lead you into doing. It totally works. And so we can assume we ended up with 26 and 14. What's the final solution for the original biggest list? Well, it's just the sum of those. Add them together, give that back, that's your answer. So the final answer is the sum of the 2 smaller answers. That's all. So return, our answer is first half sum plus second half sum. And this is going to work, unless I made a silly mistake. Yay, so I got the 40. That was the original list. Odd size lists work just fine too. It'll just chop it in half and then like in a non-even way. That's 38, and then the empty list is 0. Okay, so this is the code. We divided, we conquered, and we built up the answer. Any questions about that before I draw exactly what happened? I think that will drive the point home one last time. But this is the magic of recursion. I didn't have to think. I just assumed this was going to work. Assumed this was going to work. I didn't care about how it was going to chop this one in half and this one in half, because it would have. I just assume it's going to give me back the 26. I'm assuming that this gives me back the 14. And it will if I build up the answer correctly. That's the magic of recursion. It's always fun. But, okay, with this in mind, let me show you how this works, what it actually did. So can I take most of this? Because I kind of want to. Let's see. All right, so here's what this just did. Here's the real way that this works. So it made these 2 calls, right? It made this list, and then recursively it called, right? It called sum list on the first half. This was the first half. So, all right, what is sum list on this list? Well, it's not of size 0 or 1, so it needs to chop it in half. So it's going I chopped this one in half. That's what the recursive call did. It made the 8-6 list, and I made the 7-5 list. All right, now it's like working on this one, the 8-6. Again, it's trying to sum it. It's, again, not size 0, 1, so it's again the recursive case, and it's going to chop it in half, try to recursively sum all those values. Does that make sense? So this is going to be chopped in half to be just the list 8, just the list 6, and then it's going to try and figure out their sums, and then it will add them up together. Okay? And so, likewise, you can pretty quickly see, I think, that this is going to go down to 7 and 5. It'll try and do those. This will be chopped in half to the lists, the two lists 3, 0 and 9, 2. Then the list with just a 3 in it, the list with just a 0 in it, the list with just a 9 in it, and the list with just a 2 in it. Okay, so these are like, this is how all of the recursion is going to get down to. It's going to, sum all of these small lists, and these are finally base cases, right? Once we get down to these leaves, these pieces down here, they're always size 1. So the thing in them is their sum. And so this is how the recursion starts unwinding. You get down to here, it's like sum all the values in 8, and the list with just 8 in it. Well, the answer is 8. And it gives that answer to whoever called it. Same with this one. It's like, all right, the sum of all the people in me is 6. It gives that answer back. Okay? And all of these are going to do this. 7 is going to give the answer back to whoever was asking it for its sum. 5 is going to give the answer back. It was this list that was asking for that, right? This will get 3 and give it back. This will get 0 and give it back. This will get 9, give it back. This will get 2 and give it back. And then these, see these answers, right? Those were its first half sum and second half sum. Its final answer, now that it has those, is add them up. Add them up, give that back. That's the total answer. So what's the sum of 8 and 6? Well, divide, conquer, give back the result. It is 8 plus 6 is 14. So it gave back 14 to whoever called it. It was this call that was asking for the sum of this list. It chopped it in half, and we finally have the answer 14 for the first half. Does that make sense how it's building itself back up? And the 7 and 5, again, this was waiting on those two halves to give back answers, and now it can build it up. It can return first half sum plus second half sum. It was waiting there. So it gives back the 12. Okay? And likewise, this will give back the 3 plus the 0. And this chopped it in half, got back the 9 and the 2 finally. It can give back its final answer. Okay, the sum of everybody here is the sum of my two halves, so that's the 9 plus the 2, 11. And then finally, this original call was waiting. Oh, sorry. No, each of these. We haven't done these yet. This call was waiting for both sides to finish. Like this chopped it off. Give me that sum. This chopped this into 7, 5. Give me that sum. And now it has them. It was also waiting right here on these two calls. Now it has their answer. It can sum the first half and the second half to get its answer. That is the sum of the whole smaller list. So 14 plus 12, that's 26. And it gives that back to whoever was asking for it, which was the original call to sum all the elements of the list. And this one, again, it chopped it in half. It was waiting on the 3, 0 and waiting on the 9, 2. They have now come up with their answer by building up from the base cases, right? And now it can give back 3 plus 11 as its final answer for its sum. Okay? 3, 0, 9, 2. That is 11 plus 3. That is 14. Okay? And then now we are in the original call, right? And so you see, like, but now you see why you really can just assume it's going to work. Because it will. It will get down to the base case. It will build itself back up. And you will end up with 26 and 14 right here. You will get there eventually, as long as you build up the answer correctly. We just assumed that it worked. We didn't really care about the inner workings of it. Now I'm drawing it for you, but we didn't have to care. That's the magic of recursion. And so now this original call, it was waiting, right? It was waiting on, oops, come on. It was waiting on the first half. It made the first half and second half. It was waiting on getting their sums back. It just did, right? It chopped this in half. It got this sum back. Asked for this sum, asked for this sum. It finally just got them back. after all this work, now it can give back its answer by summing together those sums that it got from these recursive calls, which is 26 plus 14, which is 40, and it can give that back to whoever was asking for it, which maybe was a bigger recursive call, or it was the print function. For us, it was the print function. And so the print function finally sees 40, and it can print that as its final answer. Okay, so that, in a nutshell, is why this works, and it is an example of divide and conquer. Are there any questions about that? A bit of a complicated example, but this is a very powerful concept. You'll see it again if you take more computer science classes. Or maybe you've already seen it if you take CSCI, if you've taken CSCI 41 already. Am I good with that? So yeah, the standard example is sorting. Like this is an example of sorting a list, and that gives you one of the best running times that you could possibly get. Does it very quickly. Sorts the list. This, adding up all the elements of a list, you could have just done that with a loop, and it would have been just as fast, but this was easier to explain, I think. Okay? This can be powerful, though. Can be very powerful, and it is for sorting, for example. Okay? So that is, if there are no questions, I believe that is everything. You have your programming assignment out. Next week, of course, there's no new assignments. It's the last week of classes, and we'll just review for the final. So this was the last day with new content. And now, yeah, I think that is officially all that I wanted to tell you. So the rest of the time is yours.